So in this video, guys, I want to talk about something that we haven't talked, we didn't have time to talk about in the class, and that is horizontal asymptotes. And here it says, recall that polynomials and behavior will mirror that of the leading term. Likewise, irrational functions and behavior will mirror that of the ratio of the function, that is the ratio of the leading terms. There are three distinct cases that we're going to be looking at today, and two of them will result in the horizontal asymptote, and one will result in oblique asymptote. So we're going to start with case number one, and that is when the degree of the denominator is greater than the degree of the numerator. So here we have f of x. In the numerator, we have a polynomial 4x plus 2. And in the denominator, we have a polynomial x squared plus 4x minus 5. So in the numerator, we have a polynomial of the first degree, and in the denominator, we have a polynomial of a second degree. So the degree of the numerator is less than the degree of the denominator, and degree of the denominator is greater than the degree in the numerator. In this case, your horizontal asymptote is going to be y equals 0. And that makes sense. If we basically, we said that the leading term in a polynomial function basically leads the way. It has like more power as x becomes large, right? So here we have a leading term of 4x in the numerator and x squared in the denominator. So if we ignore these other terms, well, you know what? Let's do it properly. Why are we ignoring them, right? That's not right to just ignore the terms. So what we're gonna do, we're gonna multiply the numerator and the denominator by 1 over x squared. Okay, we're answering now the question, why is it happening that way? Okay, so here we're going to have a 4x over x squared plus 2 over x squared, and then on the bottom we're going to have x squared over x squared, and 4x over x squared minus 5 over x squared. Okay, so when we simplify each of these little fractions, we're going to get 4 divided by x, and then 2 divided by x squared, right, in the numerator. In the denominator, we're going to have 1 and then divide plus 4 divided by x minus 5 divided by x squared. Okay, so now let's pretend that our x is growing. So if we start with 10, then it's 100, then it's 1,000, 10,000, a million, so forth. So what's happening with these fractions? Well, if x equals 10, for example, here we have 4 divided by 10, 2 divided by 100, 10 squared, right? Then let's let x equals 100, for example. So it's going to be 4 divided by 100, and then 2 divided by 10,000. Okay. Then if x is 1,000, we have 4 over 1,000, and then 2 over a million, right? So as you can see, these fractions become smaller and smaller and smaller as x increases, right? And as the power of x is bigger, then the entire fraction gets smaller faster. Okay, so eventually when our x goes to infinity, these fractions, they become minute. They're gonna go to zero. They approach zero. If we look at each individual fraction, this one too, this one too. So the only thing that's gonna matter and gonna actually stay around is this one, right? So basically, uh, like if x is really, really big, then this whole thing, we're gonna have 0 in the numerator and 1 plus a 0 in the denominator, right? So it's 0 over 1, which is basically 0. That's the reason why when denominator is greater than the numerator, then it actually is going to be really big, and your numerator will become 0, so the whole thing will approach 0. That's why we have this horizontal asymptote. And that's the rule. Whenever your denominator is greater in power than the numerator, then the whole thing is going to approach 0 on both ends, positive and negative infinity. So this next slide, it just says the same thing. It says that when we have, remember the definition of the rational function, it's polynomial p of x divided by polynomial q of x, where q of x does not equal 0. And whenever this degree of p is smaller than the degree of q, we have a horizontal asymptote at y equals 0. Okay, so here's the next case. And here we actually have the opposite. So the degree of the numerator is greater than the degree of the denominator. Now, numerator has greater power. Well, in this case, your rational function will have a slant asymptote. Okay, and just a quick preview. This is what a slant asymptote looks like. It's a line, a slant line, a linear function, and your equation, your graph will follow that line when x goes to positive or negative infinity. And that's that slide says that. Now let's take a look at how do we find the equation of that slant asymptote. As you can see, in this case, it's a straight line that goes through 0, 1, and it has a certain slope, which is not 1. Actually, this is the equation of that slant asymptote, has a slope of 3 and the y-intercept of 1. How do we find it? And this is where we go back to division of polynomials. So let's go ahead and divide these using synthetic division. So 3, negative 2, 1, and we're going to divide it by 1. 3. Okay, so here's what we have. So basically we have 3x plus 1 plus 2 over x minus 1. Now, when x becomes really, really large, again, this fraction right here, this will go to 0, right? Because x is going to grow without bound. What's going to matter, what's going to affect the behavior of your graph is this portion, which is a linear function. And that is exactly why your the graph of this function will behave as a line as x gets larger. Again, around the y-axis, like in the center, it could behave differently, but on the ends, it's gonna follow this line, okay? And this is how you find it. You perform a division. All right, and case number 3. Case number 3 is when the degree of the denominator equals the degree of the numerator. In this case, again, it's the battle of the leading terms in the numerator and the denominator. Okay, so basically, again, we're going to ignore the rest of the term. So the asymptote is going to be y equals, and then 3x squared over x squared. What do we get? 3. Yes. So here the asymptote is y equals 3, a horizontal line. And here's an example. This is the graph of that function that we just saw. And as we can see that, well, it has vertical asymptotes, but then on the end behavior, your graph follows this line, y equals 3. And note that here, the graph does not cross this line, but on the right side, it actually first it crosses y equals 3, but then it comes back up to it. All right, so example. For these functions, g, h, and k, let's find the asymptotes. Well, when the degree of the denominator is greater than degree of the numerator, it's no-brainer. The asymptote is y equals 0, right? Because this term in the denominator will overpower the term in the numerator, and it's gonna get to 0. Okay. Again, for function g, there is a battle of the leading terms, and we're going to have 3. So the asymptote is y equals 3, a horizontal asymptote. Now, in case of h, we have the degree of the numerator is bigger than degree of the denominator. So this one is going to have a slant asymptote. So guys, your graph could either have horizontal or slant, not both. Okay. How do we find exactly, if we wanted to find the equation of the asymptote? Again, we would divide using the synthetic division, 1 negative 4, 1 over negative 2. So 1, negative 2, negative 6, 12, 13. And this, again, this remainder doesn't make any difference on the graph. It does not affect our graph at all. So the asymptote is 1x 1x minus 6, no square. just the first degree polynomial. It's a line. All right, so let's apply our knowledge right away. And in example 8, we say, we see in the sugar concentration problem earlier in this chapter, in this section, we created the equation C of t equals 5 plus t divided by 100 plus 10t. Find the horizontal asymptote and interpret it in the context of the problem. Well, first, the degrees of the numerator and the denominator are equal. They're both first degree polynomials. So we find basically the ratio of leading terms. So this is 1/10. So the horizontal asymptote at y equals 1/10. Okay, so now let's interpret this answer in terms of the problem. Let's recall the problem. This is example 3 in this section. So we had a tank of water that had 100 gallons of water and 5 pounds of sugar initially. And then they were pouring some water in and some sugar in. Okay, so we found the function C of t. It actually represented the concentration of sugar in pounds per gallons of water. Okay, so basically here what we found is that in the long run, when t becomes large, when t is large, the concentration of sugar in the tank approaches 1 pound per 10 gallons of water. Okay, so that is the meaning of this asymptote. So when t is large, basically when enough time passes, then the concentration of sugar will go stabilize to 1 pound per 10 gallons. All right, next example, number 9. Find the horizontal and vertical asymptotes of the function. So, okay, first of all, in the numerator, we have two factors, which is a second degree polynomial. Second degree polynomial, and in the denominator we have 3 factors, which indicates a third degree polynomial. So when the power of the numerator less than the power of denominator, the horizontal asymptote is y equals 0. Okay, what about the vertical asymptotes? Well, do we have removable discontinuity? In other words, are the factors in the numerator and the denominator that can be canceled out? And the answer is no, I don't see any that could be canceled out. So there are no removable discontinuity. So each factor of the denominator will supply a vertical asymptote. So the vertical asymptote, there's 3. There will be x equals 1 from the first factor. From the second factor, x equals -2. And the last factor gives us a third asymptote, x equals 5. Okay, so horizontal asymptote y equals 0 and 3 vertical asymptotes. And we could verify that by putting this function into our graphing utility, either graphing calculator or Desmos, but we're not going to do that to save time. So this is one of the problems that I want you to try by yourselves, and it's f of x equals, in the numerator we have 2 factors, 2x minus 1 and 2x plus 1, and then in the denominator we have 2 factors again, x minus 2 and x plus 3. Find the horizontal and vertical asymptotes of that function, and let me know if you ran into any trouble. Okay, and the last example that I wanted to show in this video is how to find intercepts of f of x. So as usual, how do we find intercepts for linear function, for example? In order to find the y-intercept, for y-intercept, we set x equals 0 and plug it in, right? So we're going to have f of 0, and we're going to have 0 minus 2, 0 plus 3 divided by 0 minus 1, 0 plus 2, and 0 minus 5. All right, so what do we have? -2, 3, -1, 2, -5. We have -6 over 10. When we simplify that, we're going to have, well, negative 0.6 or negative 3/5. Okay. So the y-intercept is, y-intercept is 0, -3/5. Okay. Now, for to find x-intercept, we set y equals 0 or f of x equals 0. So we're gonna take this function and set it equal to 0. 0 equals x minus 2, x plus 3 over x minus 1, x plus 2, and x minus 5. Okay, so what you need to remember that the fraction equals to 0 only when its numerator equals to 0. That's enough. We don't have to set the factors in the denominator equal to 0, because in fact, if they are equal to 0, the whole thing is undefined, is not 0. So we're only interested in the zeros of the numerator. So, and that happens, so zeros of the numerator are x equals 2 and x equals negative 3. Those are our zeros of the numerator. So the x-intercepts are we have 2, 0. Remember, those are points. And we have negative 3, 0. All right. So for this function, we already looked at this function. We found, did we find the horizontal and vertical asymptotes? Yes, we did. Okay. So we already know the horizontal and vertical asymptotes. We have x and y intercepts. Yeah, we're ready to graph it. So we're going to graph it in the next video.